If you guys want to follow along, look at the slides or go to the GitHub repo. I'm going to be doing some live coding here. Just go to the link on the slides and it'll be like the first post. I'm Will. I'm your TA, or one of them. And today we're going to be talking about OpenAI Gym and TensorFlow. And I'm going to try and give you like a brief introduction, hopefully enough so that you're really equipped to look through the documentation and kind of figure out the rest for yourselves. So the first thing I'm going to start with is Gym. And the way you kind of motivate a framework like Gym is you have to understand in reinforcement learning, getting direct samples from your environment and potentially millions of samples from your environment is a necessity, right? In supervised learning, the name of the game is data, but in reinforcement learning, this is all you have. And if we were to use real live samples for all of our algorithms, we'd run into a massive problem where the world simulation doesn't run fast enough. So actually simulating your environments is really key. And if we could get direct samples from our transition functions in reinforcement learning, we'd be able to actually execute algorithms in fairly real-time situations. So Gym basically came out of OpenAI, and it's the first universal library for the agent environment loop. Is everybody familiar with that loop, which is basically like, you got your observation, you take an action, the environment gives you a new state and a reward, etc. So before Gym, there wasn't really a unified framework, and this is OpenAI's biggest contribution. Is they've boiled down this really simple concept into for the first time a simple Python library to do this. Gym has hundreds of environments. I'll get into them later. They've got Minecraft, they've got Atari, they've got Frozen Lake, which is text-based environments, things you'll be using throughout the rest of the semester. And on the right there, you can see just how simple it is to set up an environment that runs Minecraft. And I'll actually break down this code in a moment here. But this is what we'll be dealing with today. So the Gym ecosystem consists of two components, one of which I think is about to be deprecated because OpenAI is kind of going under. But there's this OpenAI benchmark, which is actually really interesting. When Gym first came out, they kind of not only wanted to produce a Python library that lets you actually model the agent environment loop, but actually allowed you to compare different algorithms online. So they'd have all of their environments listed out, and every time you recorded your algorithm, they'd have a uniform framework for this and upload all of your training instances, and you could actually compare your performance of different algorithms online. So you can go check that out on Gym's website. But what we're really going to be talking today is actually the Python library. And it's a set of nice abstractions that I'll break down right now. So if you want to actually follow along with this demo, I hope you guys have pip installed, but just clone the GitHub repository and install it like this. You can find the rest of the info on the slides. And if you want to install new environments, make the slide as a reference. Just come back and if you want to install Atari or Minecraft or Box2D environments, and I'll get into what those are in a moment, just use this command right here. Okay, so basic concepts in Gym. So how do they actually model the environment loop? They have this gym.env class that's built in. So the sample syntax right here is like if I wanted to make an environment that played Miss Pac-Man, I would env equals gym.make. And you get your initial state, your first observation from the environment, just using this m.reset. So that'll just pass that state down to the agent. The next thing that's kind of important to understand is that if you're trying to make agents that act in arbitrary environments in Python, Gym really provides a bunch of nice abstractions to allow you to actually grab things like the action space dimensionality. So like, if my actions are discrete or they're continuous, it lets you grab the state space dimensionality. So if I have a bunch of pixels, it'll give you the resolution, and this will actually come in handy later. And additionally, you can actually sample random actions. So when we get into epsilon greedy exploration strategies, this line of code is actually going to be really useful. And the last piece of it in Gym is this transition function. It's simple as you think it is. You take a step in the environment just by passing in an action vector. So just to show you what this kind of looks like, I'll go up and code up a little demo here. We're going to try out this environment called Mountain Car, which we'll be using later in the demo when we're doing TensorFlow. So just to make your environment, you do env equals gym.make. And then the name of the environment. So these things can actually be found online. I'll post the link later. But Mountain Car is this really simple environment where you have this little cart and you're basically trying to move it side to side until it gets to this flag. You'll see in a moment. So we've got the environment made, and now we want to actually have a certain number of episodes that we're going to iterate over. So let's say we go for 100 episodes. And the next thing is we're going to reset the environment. So this will basically put the initial state of the actual agent in the environment in its right position. And then for right now, I'll just do this while true. We're going to render the environment. So there's actually, Gym is really nice. It actually renders directly to your X server. And then we're going to take an action in the environment. So the way we do this is, like I said, you just grab the environment's action space, and you sample a random action from it. In this case, the action space of mountain car is left and right. You'll see in a moment. And then we just take a step with that action. And that's how simple setting up an environment like this is. I mean, I could have replaced that with Pac-Man. Oh, I need to import Gym too. Let's do that. But you can replace this with Minecraft or any of these different environments, and it goes immediately. So this is the environment. It's taking random left and right actions. It renders to your screen. It's actually pretty easy. So we figured out how to take steps in the environment, but it's really unclear, how do we actually use the observations from the environment? So the m.step function returns 4 values. So one, it returns the observation, which is a representation of the agent's view of the environment. So essentially, in like partially observed environments, like let's say you're in Minecraft, you don't know the whole world state, it's going to give you the pixels. It'll give you like a nice 3D tensor for the pixels. In addition, a lot of these environments come with rewards baked in. So in that mountain car environment, the reward was 1 if I get my car all the way up to the flag. But again, if you actually want to get into this and you want to start making your own environments, it's super easy to just override the environment class, the gym.env class, and specify your own reward function. In addition, there's this done variable which returns, which basically specifies whether or not the episode has reached a terminal state. Like, have we actually gotten to the flag? And this is important when you're doing value iteration, Q-learning, and basically any episodic reinforcement learning, because you need to know when you're terminating your Bellman backup, basically. And the last thing is this little info dictionary. So some environments like Minecraft will give you, like the time of day and random stats about your player. So it'll just give you a dictionary of environment-specific data. So if we actually want to use this, let's just go over here and grab the. So this is the wrong demo. Okay. So we're just going to go grab the observation, the reward, the done value, and the info value, and we'll just print this out so you guys can get a taste of what's actually happening here. Okay, so basically what it's actually giving, and I'll kind of walk through this environment in a second, is the first component of each vector is the actual position on the map of the agent. So you can actually boil this environment down to linear regression. We'll see in a moment. But the position is between -1 and 0, and 0 is where you're at the flag. And then the second component of this vector is actually your velocity. And so the idea is you're supposed to be able to make an agent which only takes in position and velocity and can output whether or not it should go left or right in order to get maximum reward here. So this is basically how you get the observation. It's really straightforward stuff. But Gym also comes with a lot of really interesting additional features. So there's these things called wrappers which let you specify the maximum time in an environment. They let you change the reward function. But one of the really powerful wrappers is this thing called a monitor. It's super simple. So you make an environment, and then you decide, I would like to monitor it. And what it does, it actually records the renderings from your environment. So if you're running this thing on like a GPU server, which you will be later, you're not going to have access to the screen. So you won't actually be able to see what your agent is doing. When you monitor the environment, it'll save all of the videos of your agent to a certain directory, and you can watch it. So I'll just go try this out over here. It's dead simple. So I just say mviz, and I'm going to wrap it. Gym.wrapper.monitor. Take the environment. I want to output my videos to the same directory. And then this force equals true. I just have to do it. Don't worry about it. So what this is, well, I got to put a m.wrappers. There we go. There we go. So this will load up here, and I can't spell this. Save it. There we go. Cool. So what it's going to do right now is it's actually going to render these videos. So if I weren't actually rendering with this m.render call, it would put these videos right into the directory. So I'll wait for the video to finish recording. And you can see it outputs the videos right here. So you can use this at any time later. And that's what's really nice about Gym, is it also records the rewards too. So if you wanted to go back and look at your average episodic reward, you could do this in the same JSON file that it outputs. Okay, so the other really nice thing is I invite you to go actually to this website right now and check it out. There are hundreds of environments. So you got classic controls, so like balancing like a little stick on a cart. You've got the mountain carve environments. You've got all the Atari environments. You've got a ton of board games. You'll be using one of them on your first assignment. Minecraft, Doom. There's meta machine learning tasks, which are actually really interesting. So like one reinforcement learning task could be choose the learning rate for a CNN, given what X, Y, Z. And so your reward function in that case is the negative or the inversion of the loss, right? So you want to maximize or minimize your loss. And so you can actually set up meta machine learning tasks. And they're all built up into this environment wrapper. In addition, there's this thing called OpenAI Universe, which basically, for those familiar with it, wraps VNC, and so you can basically do any game or any environment that you could imagine doing a remote desktop in. So you can do all of the Steam games, like it's all up there. It's really, really powerful and a great benchmark for if you're writing reinforcement learning papers. So I think that's it for Gym. Does anybody have any questions? I mean, it's probably the simplest framework I could teach you guys. Okay, cool. So now we're going to move on to TensorFlow. So what's TensorFlow? So essentially, there was the period of time when there were absolutely no deep learning frameworks. And the way you would implement things is by essentially writing out all of the forward computation in a neural network and then manually writing out and computing the gradients. So TensorFlow changes that by essentially providing a graph computational model of deep learning. And what it lets you do specifically is it lets you specify this computation graph. So on the right here, you're seeing an animation of a neural network with a ReLU layer followed by a logit layer with a loss function. So you specify this thing out in code. And TensorFlow's backend will optimize this computation graph and also compute the gradients. So this has like actually been a huge problem. I don't know if any of you have implemented something in NumPy, like a neural network in NumPy, but I'll give you a motivating example here, right? So like, using NumPy's new @ syntax, I can really write a neural network in 4 lines, right? So I have some input vector x, I've got some weights w1 and a bias b1, weights w2, bias b2. The first net is the weight matrix multiplication of that by the input vector, and then you apply some activation function s. You go down here, do the same thing over and again, you got the output. Now if you're actually trying to do deep learning, you want to do gradient descent on the weights. That turns out to be a pain in the ass in NumPy because you actually have to manually write out the expressions for the gradients here. I don't know how many hours I've spent debugging before I even knew about TensorFlow, just like, is my gradient correct? Why am I not learning ... like manually computing the gradients? It's a pain. So like in this case, right, you would have some loss function L. I haven't written it down, but in this case it's L2 loss between output and some variable labels. You compute the derivative of the loss with respect to output, you get output times label, and then compute the derivative of the loss with respect to the weight matrix W2. You just take that first derivative, apply chain rule, etc. I won't go into the details, but it's a pain. You have to do this for every single variable. TensorFlow changes this in kind of a very similar way. You have a feed forward model, right? You have some input vector x, you do the normal weight matrix multiplication. In this case, I'm going to be using TensorFlow's sigmoid. And you'll see why you need to do this in a second. It just signals to TensorFlow that you're actually using it. And then for optimization and doing gradient descent, which is going to be super crucial, I make an optimizer. I'm going to use the Atom optimizer. It's just an adaptive stochastic gradient descent method. Specify a learning rate. And then I train it by just saying optimizer.minimize my loss function. That's it. You're done. And this is essentially how all deep learning frameworks work. But in TensorFlow, there are some substantial differences. So I want to kind of get into that now. So how does TensorFlow work? So there's basically 2 phases to a TensorFlow model. Actually, does anyone have any questions at this point? Is everything kind of clear? Cool. So there's 2 phases. You have construction, where it's basically you specify to TensorFlow's backend what the graph topology of your computation looks like. So I might have an input, and then I have a reshape, and then a matrix multiplication, bias, et cetera, et cetera, et cetera. You specify this. And then there's execution. So essentially what you do here is you specify to TensorFlow, I've finished constructing my graph. I want you to optimize the hell out of it. I want you to put it on the GPU, whatever else. It'll handle all of this in the back end. And then you can execute these graphs with something called sessions. So I'll just kind of break down how each of these work. So in the graph construction, there's 3 things I'm going to cover today. So Where would we start? We're going to start with how do we input data into our graph. And this is with TensorFlow placeholders. So they allow you to feed any arbitrary data into your computation graph at execution time. And just to start it off, let me just make one x equals tf placeholder float. So you specify the data type and the shape, et cetera. We'll get it to in the demo. And that's it. Now, if you want to actually put variables on your graph, like a weight matrix multiplication, there's this other handy class, tf variables. And it lets you put in different parameters that are either trainable or untrainable and specify initializers. So let's say I wanted a random normal variable, I can specify that, uniform variable, constant variable, et cetera. So just for this example, I'll make a random variable w, and then I'll make a constant variable y. And now, so right now, we're not doing anything with these variables. We just wrote 3 lines of code, and they're there. What we can do now is apply different operations to them. So basically, you have these operations. They'll take in a variable. They can be fed into other operations. And just to give you an example, if I wanted to add 2 variables in TensorFlow, I just specify z equals tf.add xy. And then I want to multiply them. I do this .mul. And my computation graph is built. But right now, there's literally nothing that I can do. I can get you the value of mult because w doesn't really have a value. All I'm saying is w is just this random normal variable. Is everything clear up to this point? What's up?
Your example of how concise TensorFlow is, you didn't use like df whatever for multiplying matrices. Does it automatically do that?
Yeah, so they've overridden all the operators, which is really nice. So you don't have to think about it that much. If you're doing really complicated things or you're using like very deep learning specific things like ReLUs, et cetera, you're going to use library functions. There's another framework, PyTorch, which I also recommend. It's more of an academic oriented framework, I think, for different reasons. And it's basically all NumPy syntax throughout the entire thing. So cool. So we've made our computation graph and we want to execute it. So here's our computation graph. And the core of execution is this thing called a TensorFlow session. So we've built the graph, 4 lines of code, or 5 now. And so sessions basically handle all post-construction interactions with the graph. So if I wanted to feed a value into the placeholder, if I wanted to see what value z had after I fed like 7 in, et cetera, the session will handle that. So we're going to call this run method of the session to evaluate tensors, and it kind of looks like this. So we make a session. This will allocate memory on the GPUs. It'll take the computation graph that we already have and optimize it. So if we do stupid redundant stuff like add 5 times, it'll condense that into one GPU add. And now what we're going to do is we're going to run this global variable initializer. So we can actually fill in w and we can fill in y. So what this does is it'll go to all the variables with initializers and actually plug in their values. We get a random normal variable with mean 1, standard deviation 2, and actually get 1.68 out. And now let's say we wanted to actually run the multiplication operation. We actually want to know what happens. Well, we still can't because we haven't fed the placeholder. TensorFlow, this is really, really simple. You just specify that you would like to evaluate that run, or evaluate that operation. And you feed into the graph right here the value of x that you want. So in the case of a neural network, we're going to feed x. We're going to feed like an image, for example. And so just running through this example, we have 3 here. TensorFlow will automatically specify in a topologically sorted way how it's going to evaluate your computation graph. So it's going to first do the add. So we're going to do 5 plus 3, that's 8. And then we're going to do the multiplication. And this is it. This is all of TensorFlow. It's this simple. But the benefit of having a graph computation framework is that it optimizes things on the fly. You don't have to think about anything going on underneath. Additionally, there's really high-level functions for deep learning. So there's these different contribution modules and different first-class places where you can actually specify like a whole deep neural network very easily. So let's say I had a placeholder x in this case. I would just say I want to do convolution to it. That easy. I want to do a max pooling conv, et cetera, et cetera. You just specify this, and the graph is fully built out for you. So does anyone have any questions about the conceptual basics of TensorFlow at this point?
This might be specific, but is there a way to actually visualize the graph of the TensorFlow?
I will get to that. It's the best thing about TensorFlow.
When you have like max pooling, is it going to construct an entire graph or have one node that implements max pooling?
Right. So actually, there's this thing called variable scoping, and I might touch on it a little bit. But essentially, in any of these frameworks, there's going to be subroutine calls. So what it'll do is on the graph, there'll be this max pool node. And then you'll be able to expand that node and look inside, and you'll see, okay, like it's doing a stride, it's doing, but you can look at all of the low-level internals, just like all the way down to the GPU kernels.
So this TensorFlow automatically computes the gradients for you?
Yeah, so that was the whole thing, is that you just specify an optimizer, and it uses this method called automatic differentiation. I can get into the technical details offline, but yeah, it'll do it, and it'll do it in order the number of lines of code you took to write your program. So it's really, really fast.
What's the difference between constant and variable?
So it's constant. So okay, so variables are. Let me just at a high level. Every single node on the graph we're going to call a tensor. That's what they like to do. That's their naming convention. So the difference between a variable and a constant is a variable is like a catch-all for any single tensor that can attain a value after it's been initialized. So let me give you an example. The random normal thing attains a value of 1.68 after it's been initialized. The constant variable we had there attains a value of 5 after it's been initialized. And the constant piece is really an initializer. So when I actually wrote like x equals tf.constant 5, TensorFlow is just making it prettier and essentially saying x equals tf.variable, and then inside of the actual parens right there would be tf.constant initializer 5. Does that make any sense? So it's just a wrapper for anything that can be initialized. Cool. So you good? Cool. Any other questions before we move on? Sweet. Yeah, it's pretty simple stuff. Okay, so let's try and actually build something out with this. So we're going to actually do behavioral cloning. I don't know if you have had a chance to play with this, but essentially behavioral cloning is just supervised learning in a setting where you have an agent. We're going to try and make an agent based on my expert playing data that's going to be able to solve Mountain Car. So first, I wrote this in the repository. You can feel free to download it and try it yourself. We're going to try and basically clone some of my data. So I made a recorder that's going to let me play this game with the arrow keys. So it's going to load up this thing, and it's going to record every single key press I do. So let's say I want to go left first, and then I'm going to go right. Okay, so that was a shitty one. Okay, cool. We solved it. Let's try it again. So you want to get more than 100 samples. I feel like that's a good thing to do in this case. But it's really low dimensional, and you can solve this task with linear regression if you think about it. So here we go. So I've solved it a few times. One more time. Let's hope it's better. Damn it. The great part about reinforcement learning is it's really an excuse to play video games. So if you wanted to play Minecraft for 5 hours, you could do that and then call it research. So let me save this data out. It's saved. We've got the data. So I've kind of basically, obfuscated, or not obfuscated, I've hidden all of the data loading and wrangling because I don't want to spend time on doing that. And what I'm going to focus on is two things: creating the model and creating the training step. So let's go ahead and do that. So I'll just run through the main method here. I don't have a lot filled in, and I'll fill in some more. But essentially, what we're doing here is we load this data using my process data method. So it's just this really long vector of states, and each state is really just a two-dimensional vector. Like I said before, position and velocity, and then actions are these either 0 or 2. That's just the quirk of the environment. So just two integers. So I load up this data. I'm making a mountain car environment. I'm specifying the steps to 1200 because when I was coding this beforehand, I was so bad I couldn't solve it really quickly. So the maximum steps are 1200. And then we've got our normal environment loop. So basically, I'm basically saying at the initial part of every episode, we haven't finished the episode. I want to get the first observation of the episode, render the episode, and then we're going to fill in some stuff to actually give the action. Right now, there's no action. So how do we do that? We're going to first create a model. And this model is going to return the state placeholder, so whatever the input to the computation graph is, the action, which should be an integer either 0 or 1. I'll multiply it by 2 later. And then the logits. So we're going to basically do like a normal softmax classification problem, maybe with a 2-layer neural network. And we'll need the logits later. I'll explain why that is. Okay, so we're going to create the model. So first thing, we're going to make the state placeholder. So I didn't really show you before, but if you want to have a placeholder with more than a a scalar value, you actually have to specify its shape. So TensorFlow float 32, it actually does matter which data type you choose here because your GPU likes certain ones more than others. So we specify float 32, and then we're going to specify a shape of none comma 2. So basically in TensorFlow, when you want to have some sort of dynamic size feed into your network, let's say we wanted to actually train this neural network using batches, right? And I wanted to specify a batch size of 32 or 100 or 150. There's this thing in the shape definition which is like kind of a wildcard shape. So this none right here is going to represent the number of elements in our batch, and this 2 is going to represent the size of the state space, which is position and velocity. And I shouldn't minus equal an undefined variable. Okay, sweet. So we made our state placeholder. We don't really have to do any pre-processing because I'm lazy. So let's just go ahead and make our first hidden layer. tf.layers. So this is the layers abstraction I was talking about, and we want to make a fully connected layer. It's going to take in the state placeholder tensor. It's going to have 128 neurons, and the activation function here, I spelled that right, okay, is tf.nn.relu. Okay, so you could do .sigmoid, you could do tf.identity, you could not even specify it, it would be a linear layer, etc. That's super easy. I want to make another one of these layers. Make sure I input the right tensor here. Cool, and then I want to actually make the final output layer. I'm going to call this logits. Does everybody know what a logit is? Or does anybody know what a logit is? Who knows what a logit is? Raise your hand. All right. You. Tell me what a logit is. Explain to the class.
Well, logit is a function from the linear line to an interval between 0 and 1 to do some classification work.
Close, yeah. So a logit basically, I mean, the name really comes from it's basically the pre-image of the softmax function. So it's basically the input to the softmax function. You'll see this a lot in TensorFlow code, and it confused the hell out of me the first time I saw it, but it's just like, it's the net variable. So we've got logits, so we're going to make another layer of dense. Here's .dense, hidden, and there's 2 outputs here. And then if we want to take an action here, we need an integer, so it's either going to be left or right. So we're going to just do tf.argmax. The input is going to be equal to logits. And the axis we're going to do it on, we don't want to take the argmax over the whole batch. We want to take the argmax on the state. So it's going to be the second axis. Is everything clear at this point? Cool. So that's how easy it was. I just made a neural network. Done. Now we've got to train the neural network. Like I said, it computes the gradients automatically. But we're going to have some input for the labels. So I'm going to make a label placeholder right here. tf.placeholder. And so the labels I've stored in my file are integers between, I think it's 0 and 2. So let's make a placeholder right here. So tf.in32. And the shape, well, it's not none, but it's a variable shape. It's the number of elements in the batch. Got it. So we've got these labels, and in our classification problem, we want to use softmax over a dimensionality of 2 outputs. So what we're going to do is going to convert them into a one-hot vector. And the way we do that is we just say one-hot labels. tf.onehot. So this will just basically put all of the different labels into a bin. So the indices for the bins is going to be tf.cast. So this is, I'll explain this in a second, label placeholder to tf.in32. And then and then depth is equal to 2. Okay, so how does this work? So this cast is actually kind of unnecessary here, but I wanted to bring it up in case you actually have inputs which you've normalized before. So let's say you're doing an integer division on your label placeholder, and it turns out that somehow TensorFlow made that a float. It's always good to just cast your labels to integers before you put them into a one-hot. And for those who aren't familiar with a one-hot, basically it'll map the integer 1 to 0, 0 comma 1. It'll map the integer 0 to 1 comma 0, and that's basically it. Okay, so we've got our label tensor right now, and then we got to define a loss. So again, TensorFlow has really wrapped this up, but you'll find later in the semester when you're doing policy gradient. Yeah, what's up?
Oh, so a quick question for so when you define layers, what does like .dense mean?
Got it. So tf.layers is a package. So, and in that package, there's this function called dense. So dense is going to be a fully connected layer. So it takes in this input state placeholder, which is this vector of size 2. And then it maps, yeah, I didn't even explain this. Thanks for catching that. And then we're going to have 128 hidden units right here. So what this will do is it'll actually make a node on the computation graph, which is composed of a weight matrix multiplication, a bias add, all the initializers, and everything. So,
Question?
yeah.
Is the add max operation differentiable?
So it's not, but I'm not going to make my loss in terms of that. So so basically this is just a convenience for me, so that when I want to run the agent forward, I can just get an integer out and plug that right into Gym. But what we're really going to use is this logits thing, and we're going to apply cross entropy to it. So that's a classification loss, which basically says I want these two output neurons to build a probability distribution essentially over them. So basically it's like you define this loss in terms of the labels that are going to be these one-hot vectors, and you say when the agent is in a situation when it's like, let's say, on the far left, and I made a movement to the right, I want my label in that case is going to be 0, 1, and I want my probability distribution generated on these logits to be 0, 1. I want the output of those neurons to be 0, 1. So it's just a special loss that says that. You had a question? So this is all packaged in here. I could specify that with an argument. So this is going to be just with a normal distribution. And it's going to be like -1, 1 truncated with standard deviation 1. What's up?
Could you do it yourself if you want?
Oh yeah. So I mean, like back in the old days of TensorFlow, this is why I think PyTorch got a lot of steam. Is basically like you had to write everything by scratch. So I would have to do tf.variable, and then I would like tf.random uniform, like 0, 1, shape equals, and then I literally have to specify, well, I've got 2 input dimensions and then 128. And then I would go and, let's call this W, and I would say my hidden output is equal to tf.mapmul. I mean, this is what you had to do. And you can still do this. Like I said, so this is a really high level abstraction over building neural networks, but when you're doing stuff like DDPG or policy gradient methods, you'll see later in the semester, you kind of have to get your hands dirty and specify some custom gradients. So you'll have like an actor and a critic. Don't need to know what those are this far, but you'll be differentiating between the critic and this actor, and you have to do a bunch of custom stuff that you'll specify. So it just gives you, it's like if Python give you access to its internal Python or C++ implementation. So.
Someone wants to do their own optimization, not the default optimization method. So one has to access the weights and gradients. So what are the syntaxes to access the weights and gradients?
Got it. So in that case, so this dense thing actually is just a wrapper. So there's this class. So I'm going to give you the 2 perspectives. One is I could just write out all of the weight matrix multiplications and do that really annoying thing. The other thing is this dense thing is just an imperative wrapper for a class called tf.layers.dense. And what that actually gives you access to is the weight vectors, the bias vectors, etc. And then when you're going to do your optimization, so I was going to define a loss here. I'll just say it's L of label and logits. I'll come back to this when we continue the demo. But let's say you want to do so you want to do your own optimizer in the sense that you want to do stochastic gradient descent custom stuff, or you want to specify the variables. We can do both.
Not a stochastic, yeah, let's say a type of stochastic.
Okay, so yeah, so I would do, I mean, let's say like, I'll make my optimizer, which is equal to tf dot, I can't remember the libraries right now, but optimizers dot sgd optimizer. And then I specify a loss. I can then do interesting things in here. I could actually go and modify certain portions of this SGD optimizer to accomplish something that I want to do. So let's say I wanted to clip all of my gradients. So then I could say gradients is equal to tf.gradients loss, and you'll have to have a list of all the weights in your neural network. So I'm really getting into the nitty-gritty here. But you could store lists by actually just going to these dense things, getting all the weights, putting in a list. So you've specified your gradients here, and then I want to clip them. You could do a tf.clip this gradient between, I want all of the values between 0 and 1. And then I would go optimizer.minimize. We can talk more about this offline, but this is the gist of it. Like, at every single level here of abstraction, you can inherit the object-oriented framework. You can write it all from scratch on your own. At the end of the day, it's a computation graph, and you'll be able to see what I'm talking about when we actually visualize this stuff later. Does that answer your question? Yeah. Cool. Any other? Yeah, what's up? Say that one more time. Pre-trained. So okay. So the great thing about TensorFlow is there's two things here. There's this actually saver and restoration library in TensorFlow. So like with 3 lines of code, you can restore from an existing model that you've saved out. And additionally, there's like hundreds of implementations of VGG, like ResNets, like DQN. I mean, you could do this class effectively that way. We'll catch you, but you could. So you could take those models and restore them. There's like some syntax. I'll just point you to it. Look up restoration initialization in TensorFlow. Cool. Okay, last question, then I'll. One more time? Yeah, dude. How big? We can keep. Good? Okay, cool. No problem. All right. So I'm going to try and get through this demo. So now we need to specify a loss. Okay, so how do we do this? Well, I'm going to use the softmax with cross entropy loss. I'm going to assume you guys know what that is. Okay. So tf.losses.softmax. Don't worry if you don't know what it is. It's just basically like I want my labels to look like, or I want my logits to look like my labels. So I define this loss right here, and then my one-hot labels are going to be my one-hot labels, and my logits are going to be my logits. So I'm just doing named quargs here. And then for good measure, if it's not, so basically it's going to compute the softmax across the entire batch. I want to reduce the mean of it. So basically I want to, over the entire batch, minimize the loss on average across every single state action pair. So the loss is going to be essentially tf.reduce mean. So this is how you take a vector of shape none and reduce it to a vector of shape 1. So you reduce the mean of the loss, and that's it. Then we're going to make our optimizer. So we're going to use the atom optimizer. Running rate -3. And then we're going to minimize our loss. So this is exactly like the demo, the example I showed you before. And this is going to be our train op. Okay, is this part clear to everyone? We're just going to minimize loss? Good, got it. Okay. So now I'm gonna do some boilerplate here. So basically we build out these methods. So right now we're gonna create the model. We're gonna call this method. We're gonna pass in the logits to that method. And now so we build our computation graph out. We actually want to make our session. So this is gonna compile it down to the GPU instructions on my laptop. Then we're gonna want to run the global variable initializer. So sys.run tf.global. Okay, and so now the computation graph is all initialized. We've got our environment. We're good to go. So now what I want to do is every single time step, I'm going to train the model, and then I'm going to get the action. Does anyone have questions really at this point? Cool. So to train the model, so first I'm going to copy some boilerplate code here. So I've got this data right here. I'm going to get a state batch and an action batch. So this is just basically like my features and my labels. That's it. So just pretend like I've gotten this batch. Now to actually train the model, I'm going to evaluate the train operation. So this is this thing I got from creating the training right here, this train op, this minimization op. And then I also want to get the loss every time step. Okay? So I'm going to run both of these things in parallel in the same instance of the computation graph. So this is important. So if you wanted to run 2 operations, one after another, you would do 2 sess.run calls. If you want to evaluate a bunch of different tensors on the graph at once, make a list and put it into one. So you can do things really efficiently this way. So then I'm going to basically, so I've got this. And now I need to feed into the computation graph, I need to feed the states in and I need to feed the labels in. So this is as simple as my inputs are x in this case, so I'm going to put my state data in. I'm going to put my labels in. And additionally, I want to actually get this loss and print it out. So what I'm doing here, so the sess.run is going to return the output of train and the output of loss. Train has no output. Like when you evaluate the minimization operation, it's just going to do it and then return none. The loss is actually going to return a value. So I'm just unpacking this tensor here. I'm going to call it cur loss. So let's print the loss. That's good. And we finished training. That's it. That's all it takes to train this model. I mean, it's like I've written 50 lines of code and we've got a fully working, hopefully working, deep learning model. What's up? Oh, thanks for catching that. Yeah. I mean, it wouldn't matter in this case because I've recorded like 142 samples, so my batch size is what it is. But yeah, so okay, so now we've trained the model one iteration. Let's actually get an action from the model and run it on the graph. So same thing. So I got this argmax before because I actually wanted to use, let's see, where's the argmax? I actually wanted to just plug the integer straight into OpenAI Gym. So this action right here, if it's a discrete action space, is just going to be an integer. So in Pac-Man, it's like 0, 1, 2, 3, 4 for like left, right, up, and down. In this case, it's 0, 1 for left and right. So I'm going to evaluate the model. So this is pretty simple. That's a tensor I want to evaluate. And then my feed dictionary is going to be, well, in this case, I'm going to take the observation. So this is just an output from OpenAI Gym. I think from this environment, the observations are like wrapped. So it's basically a tensor or a matrix of size 2, 1. I just want to flatten this and make sure I can feed it into the model. This is just like boilerplate. And then really, so this is a good times to kind of notice this. So the model, I specify the output is going to take, or the input of the model is going to be none, 2. And I'll do a bunch of operations on that, and then I get the argmax. But can anybody guess what the shape of this action is going to be on the computation graph?
Horizontal vector.
Okay, horizontal vector of what size? So the batch size, that's right. So it's going to be, so the problem is it's the batch size. So when we're feeding in this observation here, one thing I did and I didn't tell you guys about was that I made a list of a single observation. I made a list of size 1 of the single observation because I need to make sure that the tensor that's going to the model is actually none, 2. So none in this case is going to be a wildcard for 1. So there's a list of size 1 going in batch, and then because of that, the output of the model is going to give me a list of size 1 because there's a batch size of 1. So I'm going to grab the first element of that. That's just going to be the integer. And then don't worry about that times 2. That's because I screwed up in the environment. And that's it. We're done. We've completed the actual demo here, and we can actually run it now. So let me see. So let's try it, Python 3. And then /data. It's saying I don't have a GPU. And then we can see the loss going down, and that's it. And it's learned directly from my data. It's really satisfying to watch this. Unless I played poorly. No, it's got it. Cool. So there you go. That's behavioral cloning. But I haven't gotten to the best part of TensorFlow yet. Like this is all great. You can do this with any deep learning framework. What you can't do is this visualization piece I'm going to talk about in a minute. So there's this thing called TensorBoard, which I've kind of baked in the code. You can go check this out on the GitHub repository. I've kind of baked this into the complete version of the demo. But essentially, it lets you, yeah, what's up?
Sorry, before you move on.
Yeah.
So you set the action twice. You set the action earlier in the model, and then you set action equal to that sess.run comment. Are you actually overriding an action, or is this a different action?
This is, yeah, it's a different action. It's because it's up here in the scope. So I could have called this like hot dog.
That's within the model. That's its own. Okay, that's the output.
Yeah, yeah, yeah. Yeah, I mean, it's whatever. So the actual tensor that I'm using in this scope is called model. Yeah. So we're evaluating our hot dog, and we're doing well. I mean, he's hit the loss right now is 0.11. We're good. Good enough for me. Okay, so this is the best part about TensorFlow is this thing called TensorBoard. Lets you look at like certain tensors I've logged over time, and it actually lets you look into the computation graph. So this is like the last thing I'm going to show you guys here. So this is the complete version of the demo. It's literally the exact same thing, except I've written this line here, and you can go look up how to visualize your data in TensorFlow, but it's this summary scaler, which basically I want to keep track of the loss in TensorBoard. And what this ends up looking like is, I'll stop the training here. I'll run the tool that comes with TensorFlow. And I think it should be logs. So I'll launch up TensorBoard, and like, once I saw this, I was just so sold on TensorFlow. So this is TensorBoard. If it loads, the computer's dying. Come on. Cool. So first thing is I kept track of that loss variable. Here it is. So I didn't have to do any of this crazy matplotlib stuff. Like screw that. We're too good for that now. We can track the loss. We can track the different variables of the weights over training. We can track the gradients. I mean, this is literally the best way to debug deep learning models. Like, you don't know how many hours you could spend just like, are my gradients right? Like, what's going on here? This will lay out everything for you. You can check if your values are normalized and everything. If you're doing like image data, you're doing GANs or something, this thing will actually keep summaries of the images in your model. So like, let's say you wanted to see after 500 iterations, is the GAN producing cats or just white noise? And you can actually tell. You can do that same thing for audio. I mean, Google's really backed this because it's the main debugging platform for a lot of their deep learning engineers. And this is why it's such a good framework for if you're trying to do really industry level deep learning. But the greatest part about this is, let's say you like messed up one line of code and you're like, why is my model outputting like 0? Just constantly 0. Well, the easiest way that could happen is you just forgot to link something up. Like I could have gone in my code over here and then, let's see right here. I could have gone in my code in this model section, and I could have just said, here's the first hidden layer output, and I could have said this is also the state placeholder. And there would be a break in my computation graph. Like it just wouldn't work. But I'd have no idea why the hell that wasn't working. So what it lets you do is we can literally this is like the exact neural network we built. You can expand the computation graph. So this was that tf.dense call we made. And inside of dense, you can see what TensorFlow is doing underneath the hood, what you could override. So there's this kernel and there's this bias. So the kernel is going to be your weight matrix. They map multiply with the placeholder coming in. You add a bias. You apply a ReLU. Well, I want to know how they're initializing the kernel. So like you can open up all of these different subcategories, et cetera, and explore. So it's just like by far the best way to debug your model. In addition to all of this, you do histograms in TensorBoard. You can literally visualize word embeddings. Like it's all here. So I think that's it as far as the demos are concerned. I mean, I point you to TensorFlow's API references. I mean, if you have any questions, please let me know. All the slides again are on Twitter. So cool. Thanks.